Welcome to another lesson in our series on linear programming. In this lesson, we will use linear inequalities to describe the constraints of a linear programming problem. We'll plot the graphs of these inequalities and see how this can help us to find the feasible region. Once we see what the feasible region is, we can identify the best possible solution, the optimal solution within the feasible region. By the end of the lesson, you should be able to use linear inequalities to find the feasible region of a problem and find the optimal solution by testing the points in the feasible region. But first, let's meet a land developer who uses the processes of linear programming in his work.
Hi, yes. The problems I deal with are similar to the ones that you're busy with. Except the ones I deal with have many more variables, and sometimes that's difficult to represent on a graph. Let me show you what I mean. This is a proposed housing development plan. It has been submitted to the town council for approval. I've bought up many old, large properties in the suburbs, and I want to put townhouses down, multi-story apartment blocks and cluster houses on them.
Great! More housing units on each piece of land mean more homes for people. And since we have a housing shortage, it makes sense to make better use of the land, especially closer to town, so that people don't have to travel such long distances.
Unfortunately, many people in neighboring suburbs don't agree. They're worried that the densification of the area is going to bring down their property values.
Densification? What's that?
It has to do with the number of people living on each plot of land. Now, as a land developer, I want to increase my profits. So the more housing units I can put on a plot, the better. So it means that there are more people living on each plot of land than in the surrounding areas.
And the people objecting don't like that because?
I guess they're concerned about the increase in noise and traffic in the area. Some of them are probably also concerned that services like water and sewage and electricity are going to become overloaded. From an environmental perspective, we'll be cutting down trees and replacing them with houses. And so the area is probably going to be less pleasant for them to live in. And so they're worried that this is going to decrease their property values.
So how do you resolve that?
Well, there are various factors which influence our decision-making process. In linear programming terms, you'd call these constraints. Now, one of the constraints is what the land has been zoned for. In cities, land can be zoned for industrial or commercial or residential use. In the case of residential zoning, there are also regulations that determine what kinds of houses can be built. In certain instances, only freestanding houses can be built, while in others you can build townhouses and flats. So firstly, we need to make sure that the project meets those regulations and constraints. And we also need to make sure that we take into consideration the concerns of the people living in the surrounding neighborhoods.
It sounds like things can get very complicated.
They can, but it comes down to finding a solution that considers all of the constraints and yet maximizes the benefit for everybody involved. The people that need the housing, the land developer, as well as the residents in the surrounding suburbs.
It seems that the land developer has some tough choices to make. Fortunately, we don't need to consider all the constraints that he must consider. In this lesson, we'll look at a building development problem, but we'll only work with a few constraints. So our problem is simplified and not completely realistic. I've also chosen to work with numbers that work well to illustrate how linear programming works. Here's the problem. A developer has 10,000 square meters of land that he wants to sell off in smaller stands. He plans to divide the land into 2,000 square meter stands and 1,000 square meter stands. He has a budget of 24,000 rand to clean up and fence the plots so that they can be sold. For various reasons, he will need to spend 6,000 rand on the larger stands and 1,500 rand on the smaller stands. According to the town council, a 10,000 square meter piece of land is suitable for up to 36 housing units. The council also states that no more than 6 housing units may be built on a 2,000 square meter stand and no more than 4 housing units on a 1,000 square meter stand. The developer wants to divide the land in a way that allows for the maximum number of housing units, but he can't let this go beyond a total of 36 housing units because of the town council regulations. If the developer expects to make 15,000 rand profit on the sale of the bigger stands and 5,000 rand profit on the sale of the smaller stands, how should he divide up the land to make the greatest possible profit? That's a lot of information, so let's work through this slowly. A developer has 10,000 square meters of land he wants to sell off in smaller stands. He plans to divide the land into 2,000 square meter stands and 1,000 square meter stands. What variables do you think we need to use for the problem? The variables are the 2 kinds of plots. Let's use X for the number of smaller stands and Y for the number of bigger stands. We want to know what combination of plots to use, what number of bigger plots, and what number of smaller plots. We know that the total land available is 10,000 square meters. So we can say the land used by the smaller stands plus the land used by the bigger stands must be less than or equal to 10,000 square meters. We've made an inequality with words here. Now, can we write this inequality using variables? Well, each of the smaller stands uses 1,000 square meters. If we multiply the number of these stands by 1,000, we'll get the amount of the land used. X is the number of smaller stands, so we can write this as X times 1,000. And if we do the same for the bigger stands, we'll get the number of stands, which is Y, times by 2,000. So, the inequality we need to work with is 1,000 times X plus 2,000 times Y, which must be less than or equal to 10,000. Now let's look at the next part of the problem. The developer has a budget of 24,000 rand to clean up and fence the plots so that they can be sold. For various reasons, he will need to spend 6,000 rand on the larger stands and 1,500 rand on the smaller stands. We'll call this the preparation costs. We know that he wants to spend no more than 24,000 rand, so we can write less than or equal to 24,000. So the preparation cost for the smaller stands and the preparation cost for the bigger stands together must be less than or equal to 24,000 rand. It's useful to write this down in words first. Now, can we put that into an inequality using X and Y? The cost of preparing each smaller stand is 1,500 rand, and there are X stands. That comes to 1,500 times X. Then the total cost for the bigger stands is 6,000 times Y. That's all less than or equal to 24,000. The next part of the problem says, According to the town council, a 10,000 square meter piece of land is suitable for up to 36 housing units. The council also states that no more than 6 housing units may be built on a 2,000 square meter stand and no more than 4 housing units on a 1,000 square meter stand. Let's call that the town planning regulations. There can't be more than 36 housing units on the whole stand, so we can write down less than or equal to 36. This total is made up of the housing units on 1,000 square meter stands and the housing units on 2,000 square meter stands. There can be 4 units on a 1,000 square meter stand and there are X of these stands, so that's 4 times X. 6 units on a 2,000 square meter stand and there are Y of these plots, so that's 6 times Y. The rest of the problem says, if the developer expects to make 15,000 Rand profit on the sale of the bigger stands and 5,000 Rand profit on the sale of the smaller stands, how should he divide up the land to make the greatest possible profit? This is the part of the problem that asks for the best possible solution. In this case, the greatest possible profit. To find that, we must first find all the possible solutions. In other words, we need to find the constraints on the options and then find the feasible region. Only after that can we look for the best solution. But we'll come back to this when we've found the feasible region. So, we've set up inequalities for the constraints. This one gives us the constraints for the total amount of land available. The second constraint has to do with the preparation costs. And the third constraint has to do with the number of units allowed on each type of plot by the town council. We can plot these inequalities on a set of axes. We'll put the number of smaller stands on the x-axis and the number of larger stands on the y-axis. So let's start with the graph for the first constraint. We can plot the straight line for the equation first and then decide about the less than part of this. We can plot the graph for this equation in whatever way we find easiest. We could find the x and y intercepts, or we could put this into a form that we are used to. Y equals mx plus c. This is the way I'll do it for now. To get into this form, we subtract 1000x from both sides. Then divide through by 2000. So, y equals minus a half x plus 5. That looks easier to put onto a graph. The graph will cut the y-axis at 5. The gradient is minus a half, so from here, we can go 1 unit down and 2 to the right. That's this point, 2, 4, and we get this line. Remember that this line represents the equation, not the whole inequality. Now we need to decide how to show the less than part of the inequality, and we need to decide which side of the line to shade. We can check a point on one side of the line. Let's pick this point, 4, 2. If we substitute this into the inequality, then 1000 times 4 is 4000, and 2000 times 2 is also 4000. That makes 8000, which is less than 10,000, so the point 4, 2 does satisfy the inequality. I always find it useful to try another point just in case I've made a mistake. Let's try this one at 4, 4. If we substitute that into the inequality, then 1,000 times 4 is 4,000, and 2,000 times 4 is 8,000. That's 12,000, which is more than 10,000, so the point 44 doesn't satisfy the inequality. That confirms that these points here below the line satisfy the inequality, but these points above the line don't. Now here's something important about linear programming. We could shade the side of the line to show the points that satisfy the inequality, but in linear programming we use a different convention. We prefer to shade the area that isn't part of the possible or feasible region. If we shade over the possible points for each constraint, it becomes difficult to see the points in the feasible region. The points will be colored over several times depending on the number of constraints. If instead we color or cross off the areas that aren't possible, we'll create a clear space that shows the feasible region. So, we'll shade this side of the line to show that these points aren't possible. Now we've been through the steps of graphing one constraint for this problem really carefully. We still need to consider the other constraints. Let's look at the preparation costs. First, we'll consider the equation only. 1,500x plus 6,000y equals 24,000. This time we'll find the x and y intercepts for the graph. For the x-intercept, y equals 0, so we get 1,500x equals 24,000. Dividing through by 1,500, we'll get 16. So we can plot the point 16, 0. Let's find the y-intercept. That's when x is 0. So we get 6,000y equals 24,000, and y is 4. So the intercept is at 0, 4. So here is the graph for this equation. Finding the intercepts with the axes is often the quickest way to plot a straight line graph. Now for the less than part of the inequality. This point, 1, 4, comes to more than 24,000, so it doesn't satisfy the inequality. Let's check a point on the other side. We'll try 2, 3 here. That comes to 21,000, and that is less than 24,000, so it does satisfy the inequality. We want to shade the part of the graph that doesn't satisfy the constraints and leave the part that does open. So we'll shade this side of the graph. Now for the third constraint. I have already plotted the graph for this constraint, the town planning regulations, and I've added it to the previous two graphs. It has taken some time to graph these inequalities, but once you have worked with more of these problems, you will see that this process is still faster than checking every point. Remember that on this graph, the shaded parts of the graph are not possible points. The clear part of the graph, the part that is not shaded, is the feasible region. In the feasible region, we only need to consider the whole number values for x and y. This is because the developer won't use pieces of a stand. For example, look at this point. He can't make 4.5 of the smaller stands and 1.5 of the bigger stands. He can only work with whole stands. So these are the possible points in the feasible region. These points still represent quite a lot of possibilities, and we need to decide which of them represents the best option. Let's look at the question again. If the developer expects to make 15,000 Rand profit on the sale of the bigger stands and 5,000 Rand profit on the sale of the smaller stands, how should he divide the land to make the greatest possible profit? Can you see a way to find the point with the greatest possible profit? One way to do this is to test each of the points in the feasible region and see which one gives us the best profit. Let me show you what I mean. This point, 4-2, represents 4 of the smaller stands and 2 of the bigger stands. The developer makes a profit of 5,000 Rand on these ones, so that's 4 times 5,000. He makes a profit of 15,000 Rand on the bigger ones, so that's 2 times 15,000. That comes to a total of 50,000 Rand profit at this point. Let's try another point. Let's choose this one here at 6-2. That's 6 of the smaller stands, so he makes a profit of 6 times 5,000. Then 2 of the bigger stands at 15,000 Rand profit is 30,000. That's a total of 60,000 Rand. If we continue testing each point in the feasible region, this is what we get. If you look at all these values, you will see that the most profit is here at the point 4-3. It works out to 65,000 Rands profit. So the best way for the developer to divide his land up is to make 4 1,000 square meter stands and 3 2,000 square meter stands. In the next lesson, we will look for a pattern in the profits that we have written onto the graphs. We want to see if we can find the best solution without having to test every point in the feasible region. For now, here's a task for you to do. Use the graphs to explain which constraints prevent the developer from dividing the land into 5 stands of 2,000 square meters each, 10 stands of 1,000 square meters each, or 8 bigger stands and 2 smaller stands.